So I'm really glad to be back here in Minneapolis, not least because last time we were here, I was the meeting organizer and I saw exactly 0 talks. So this is already a big bonus for me to be able to enjoy the conference. So the work I'm going to talk to you about today is collaborative work with my co-author Arzu Chultekin, who is an academic in Switzerland, and one of her students, Rahel, and some academics and students in South Africa, Victoria Rautenbach, Serena Kotsia, and Azile Delaney. So we've been kind of working on this project for a while. You might have seen a few other talks related to this never-ending project here at NACIS. Arzu last talked about the project in 2020 at virtual NACIS. So I'm going to give you a little bit of a story about how we got to where the study that we ran today. So for those of you who might or might not know about this, we can experience a terrain illusion when we look at shaded relief. This is obviously not shaded relief, but it shows it in a very simple context where you can see some of those little circles pop out and some of them sort of sink in. And whether you see them sinking in or popping out relates to where the light is coming from. And psychologists call this the light from prior assumption or the overhead illumination bias. And the idea here is really that most of the light that we experience in our lives comes from above, right? Whether that's the sun or the light in a room that we're in. And so your eyes, because your brain is kind of a statistical machine, your eyes sort of have this expectation of how shadow interacts with different objects. Okay, so here you can see 2 examples where it's kind of the illumination has changed. So in an actual relief context, this happens when we generate shaded relief with light coming from certain angles. So when we generate shaded relief with the traditional cartographically recommended angle from the northwest, for most terrain orientations, we would see a peak where there is an actual peak and a valley where there is an actual valley. But if we swing around and shine the light from 180 degrees opposite of that, many people will see that terrain inverted, and probably you see that here in the display. So Arzu, some time ago, did a study that looked at this kind of comprehensively. And you can see in this graph here, basically a plot of accuracy where the peak in people correctly identifying the landform that's actually being depicted in the shaded relief at basically the north-northwest angle rather than northwest, so a little bit right of northwest. And you can see that they're very poor at identifying it correctly. In other words, many, many people see the illusion at those 180-degree angles, right? So that was kind of the first study in this series of studies. And she explained it as probably being caused by this overhead illumination bias. Now, this bias also happens in satellite images, right? So this is an image where I'll just let you look at it for a second, and you tell me if that looks right to you or not. Where is the snow? Right? Doesn't quite compute, right? If we actually rotate that around, that looks a little better, right? So this happens primarily because of when we have sun-synchronous satellites, they're taking a photo at 10 o'clock in the morning to try and counteract haze and other things that impede good satellite imagery. And so oftentimes when it's taking that photo, it's coming, especially in the northern hemisphere, from a southeast angle. And so we get this inversion effect that you see here in the study. So they did, one of the questions that raises also, this is experienced much, you see this much less in images from the southern hemisphere because the aspect of the light and the way the sun is moving through the sky is different depending on which hemisphere you're in because of the way the earth tilts, right? So in the northern hemisphere, we have a southerly aspect, and in the southern hemisphere where I live, you want to buy your house with a northerly aspect, not a southerly aspect. Right? So this is why we see this differently often in the 2 hemispheres. So she did a study with a student looking at this, and also observed that we see sort of like this flipping effect. Like if we flip the image, people will often interpret that image correctly. So to sum up, what do we actually know about terrain inversions? So from this series of studies that have been done, we know it occurs in shaded relief maps. We know it also occurs in satellite images. It's prevalent, right? We can have up to 98% of people seeing it wrongly from certain orientations in shaded relief maps. And we see it in 40 to 60% of satellite images. So it's a common problem. Texture can reduce, but color can strengthen this illusion. So she's done another series of studies. The references are there. I can point you to them if you're interested. There is a thing called a left bias, which I forgot to explain actually in this graphic here. So you might see some kind of faint lines that are connecting on either side of the peak. And that's where on equally far apart from zero, people are differentially able to identify the landform correctly. And they're more able to identify it correctly on those left-hand side angles, hence the name left bias. So we know that there's a left bias that occurs. We also know that non-expert men are more confident but not more accurate in making these judgments. I'll leave you to draw your own conclusions about that. It's reproducible. We've seen it in different populations, and it can be fixable depending on how we sort of make manipulations to these to the images that we produce. So how left is the left bias? Depending on the study, it's measured to different degrees. In Arzu's original study, it was measured at 13.4. It's been measured as big as 24, as small as 7.9. It seems to possibly occur to different degrees, whether you're left-handed or right-handed. And you might say, well, why is that? And this has to do with this light from above hypothesis. Where a lot of the buildings that we build and the way we set things up is set up for right-hand people, and the way light shines and making it be convenient for them to do things like riding and other manual tasks. Left-handers might have to actually turn their bodies so they aren't shadowing things. So this is one working theory anyway here, that left-handers have adjusted their behavior to cope in a right-handed world. But why does it happen? We don't really know. There's some competing hypotheses about this. This is the prevailing one with the light. Okay, so in the last NACIS talk, we had set out to do this reproducibility study to see, does this happen in other places? Does it, and in particular, does it happen in the southern hemisphere? Because we also know that the way the sun's light is moving in the landscape is different. It's coming from a different aspect. So we were interested in this because it can affect the way shadow moves, right? Depending on where the sun is. Is it in front of you? Is it behind you? If you're looking you're all looking in the same direction. So we did this reproducibility study. And we found some kind of strange things. So this was some original data that they had collected in Switzerland. Here you can see as you get towards that north-northwest, you get the peak of accuracy. And then we collected some data in South Africa, and it's kind of similar, but the peak is actually shifted a little bit to the right-hand side. It's going further towards angles towards zero. And when we collected in an Australian study, we saw something similar to that. And we thought, that's a bit weird. But then we realized that the proportion of left-handers was different in the studies. There was only one person in the original Swiss study. There were quite a few more in the Australian and South African studies. The Swiss team ran another study with a higher proportion of left-handers, and they found data that were more similar to what we had found in the southern hemisphere. So we thought, we don't really know which is causing this. Is it the hemisphere or is it the handedness and just differences in the sample? So today this year we set out to actually try and determine this by recruiting a balanced sample. So we ran a study, we had 252 participants. It was counterbalanced across hemisphere, handedness, and gender. We were collecting data on accuracy and confidence, and we measured some other things because we were doing this study in the wild. It wasn't in the lab because we couldn't reach enough people in the lab, so we used an online platform called Prolific to actually recruit participants. This gives us some advantages that we get a wider diversity of participants than we can get on a university campus, but it comes with some experimental disadvantages, like people are using all kinds of devices with different screen sizes, different screen resolutions. They're of different ages. Age might also play a role here with vision. And they have different levels of experience with maps. So we collected some information about that. Just to give you a little bit of a sense of the stimuli that we were working with, so this is one set at one particular location, and you can see we generated these reliefs in azimuths varying by 7.5 degrees from 270, so left hand, all the way to 90. And if you look at that carefully, you should see the terrain inversion towards the bottom. Okay, so what did we find? We found there was not really much of a difference in handedness, which we didn't expect in an overall sense. I'll break it down by azimuth in the next slide. We saw quite a big difference in hemisphere, with northern hemisphere people being much more accurate than people in the southern hemisphere. And we saw basically no difference by gender. We didn't expect to see an accuracy difference by gender. Okay, so if we break this down by accuracy, by azimuth, and I'm showing you here obviously only selected angles because I can only fit so much on one slide. What do we see here? So we see in the graph on the right-hand side, we do see a little bit of an evidence of a left bias, where we see the order of the bars changing from the left-hand angles to the right-hand angles. So we see that's reproducing what we've observed in past studies. We also see that there are somewhat different peaks in the northern hemisphere and the southern hemisphere accuracy. They're not peaking at the same angle. And we see that persistently we're getting this better accuracy for the northern hemisphere folks. So what are our preliminary conclusions from this? So with the hemisphere effect, we see that the illusion is stronger for people in the southern hemisphere than in the northern hemisphere, pretty much across all the studied angles that we looked at. What we're not certain yet about, and we need to look at carefully, is whether this could have been a potentially confounding factor. We were our study area, I forgot to mention this, so we recruited people from the UK and Ireland from the northern hemisphere, and people from South Africa from the southern hemisphere. We were trying to also recruit people from Australia and New Zealand, so all three of those countries, but somehow I think when Prolific released the study into the wild, they maybe released it in South Africa first, and the study filled really quickly. So we ended up having no one in the sample from Australia and New Zealand. We know there's some biases about internet speed and screen size that we measured. And so, and there are also age biases because of different population structures in the countries. So we need to check and see, are any of those things possibly the explanation for this difference that we observed? So we're not sure yet if the hemisphere effect is a real effect. For handedness, as expected, we observed no major differences in the prevalence of the illusion, but we did see a little bit of a shift of this left bias, and the left-handers' overall accuracy is similar to the right-handers. So what are our next steps? Our next steps are to look carefully at these potential sample biases and see if they explain anything, or if we think the hemisphere effect is robust. We're going to look at some speed-accuracy trade-off. We're going to analyze the confidence data, see if there are any differences there. We're going to do the left bias calculation to see if those angles change. And we're going to look at some interactions between handedness and hemisphere to see if they explain any of the patterns we observed. So happy to take any questions, comments, observations you might have.
We have time for one question.
Either one of you know how to find me, so whoever gets picked.
Which one? Which one? Okay.
You looked at hemisphere. Have you looked at latitude within a hemisphere? The UK is a whole lot further north than South Africa is south.
Yeah, no, for sure. It's actually really difficult to control for latitude because there's not that many people who live in the Southern Hemisphere and who also speak English. So we're limited in our choices there. And we did try and control, we tried to pick areas that were not huge. So we did not put this in Canada. We did not put this in America deliberately because the latitudinal gradient was quite big, and in the UK it was much smaller. So we have thought about, in the Australian data we actually, that we collected a few years ago, there we constrained it to actually people who lived in one state to try and control that. It is something we could consider, sampling across a latitudinal gradient. That's a little harder to recruit people that way because people don't know their latitude if you ask them. And it's hard to screen for that, even in an online study. But it could potentially be an issue, for sure.
Thank you so much, Amy.